In biochemistry, we're often interested in reversible reactions. A general form of such reactions could be products A and B reversibly forming products C and D. Could be simpler, could be more complex. And there's a quantity called a chemical quotient, sometimes abbreviated as a Q, which we define as equal to the product of the concentrations of the products divided by the product of the concentration of the reactants. And this value is a way to monitor the progress of the reaction. If we start with a reaction that is composed of just A and B, then Q will be very small, C and D will approach 0. And through time, this value of Q will change. And if the reaction is one that's driven to completion or near completion, where the values of C and D are very high and A or B are low, then the value of Q will be very high. What's interesting for us is at equilibrium, which is a very important case, a very common case in biochemical situations. We're interested in the equilibrium. So at equilibrium, this reaction, that should be equilibrium, we can define an equilibrium constant that's equal to the value of the products, the concentrations of the products and reactants as such at equilibrium. And this is a constant. It's a constant that means it's a fixed value. It does not change. It doesn't matter if we add more A and B when the reaction comes to equilibrium, this number will be a constant. It's independent of the concentration of any one of these substrates. So let's apply this in a simple situation. So we can imagine a more simple situation where we might have one reactant that's in equilibrium, that's in reversible reaction, a reversible chemical change with a product. And the example I will use is that of glucose. Glucose in aqueous solution exists almost completely, more than 99%, in the cyclic form here, the 6-membered cyclic ring. It's called a pyranose. So this is a glucose, natural glucose. Common glucose is a D sugar, so this is the alpha anomer of glucose, and it's alpha D glucopyranose, and it is in exchange with its anomer beta glucose, which is very similar and differs only at the configuration of the anomeric substituent, the anomeric carbon here. So we have a 6-membered ring in a chair form, and there is an equatorial substituent in the beta anomer, and there is an axial substituent in the alpha configuration. We would suppose from our knowledge of the model system of cyclohexane and steric clashes of axial substituents that the beta form would be favored, would be energetically favored over the alpha form, and indeed it is. So what does that mean? It means that if we make a solution of alpha glucose and we allow it to come to equilibrium, and that equilibrium will take some time, but sooner or later some of those alpha anomers are going to change into the beta anomer. This process used to be called mutarotation because it was monitored by the optical activity. Both of these rotate polarized light, but they do so to different extents, so the reaction can be monitored by the rotation of light. This process will occur, but because it's a reversible reaction, any beta form in solution can also go back to alpha, and the result is that they're in exchange with each other. How fast that exchange occurs, how fast a solution comes to equilibrium, depends on whether it's a pure solution or whether there's some sort of catalyst. This reaction can be as a cyclic hemiacetal hydrolysis reformation can be catalyzed by weak acid or weak base. What's interesting is we observe at equilibrium a ratio of 36 to 64%, which means that we can describe an equilibrium constant of this reaction as 64 divided by 36, which is about 1.78. What does that mean? This is a constant. That means that if this reaction is at equilibrium, then the ratio of beta form to alpha form is 1.78. What does that mean practically? It means if I go to the laboratory and take my giant jar of alpha anomer of glucose and dissolve it in water, that with time, and depending on how clean the water is or what I add to it, it may take more time, there's going to be a ratio of alpha and beta forms of 1 to 1.78. It also means that if I happen to find a bottle of beta glucose, the beta anomer, which I have not seen available in the market, and make a solution that's pure beta and wait through time, it will also mutarotate to the same ratio. Okay, that's interesting. That's the idea of a reversible chemical process. It's defined by an equilibrium. It's defined as having at equilibrium a constant value. So if we add twice as much alpha here and twice as much beta here, the proportion will not change. And it has metabolic significance because very often in the cell, in living systems, we have a property, sometimes, let's say this relates to homeostasis. We think the states tend to be very much the same. There isn't very strong changes in the cell, despite a flux of metabolic metabolites through the system, which here I can explain as, imagine that we have an equilibrium mixture of alpha and beta anomers, and we add more alpha, say it's an upstream metabolic product, and more alpha comes into this solution, a cell for instance, and maybe there's another enzyme or downstream metabolic process that uses only the beta. It leaves the alpha but takes the beta, and beta is removed. Well, then we're constantly going to have alphas turning into beta, and not as many betas turning back into alpha, because new alphas are constantly arriving and betas are constantly being removed. But the actual ratio of alpha and beta will not change. If I may come up with a little analogy, we can imagine that we have some container and we may be pouring in water from a hose here, and water may be coming out here. The water level is going to be at many rates of flow leaving and flow coming in, constant, determined by where this hole is. And we can add a little bit of water, and a little bit of water will trickle out, or we might be able to add a lot of water, and a lot of water will trickle out. Of course, there are limits if this hole isn't large enough. So what is this? This analogy doesn't work perfectly, but this is to say that we're not surprised in many aspects of metabolism that there's a high flow, a high flux, yet the actual concentrations of metabolites are near equilibria. I will continue this in the relationship to free energy in the next part.